Artemis 2, once a distant goal on the horizon, is now just weeks from flight. Soon, astronauts will venture beyond Earth orbit, ending a 53-year pause since humans last traveled toward the moon. This mission does more than carry a crew. It introduces capabilities and technologies never seen during Apollo and beyond what Artemis 1 demonstrated. With upgraded systems and new objectives, Artemis 2 represents a decisive step forward. Here's everything you need to know about Artemis 2, the mission preparing to launch in just weeks, only on Great SpaceX. Let's begin by looking at the overall progress of the mission. After facing extensive criticism, the Space Launch System, the Orion spacecraft, and several other major components have now been fully assembled and rolled out to the launch pad. With this milestone complete, attention has shifted entirely to the wet dress rehearsal, which is one of the most critical tests before launch. In the latest update, NASA has reported several technical issues. These include a liquid hydrogen leak in the core stage and a pressure loss problem in the Orion hatch open and close support system. Among these concerns, the liquid hydrogen leak was largely expected. Hydrogen is notoriously difficult to manage, and resolving such leaks is rarely straightforward. As a result of these issues, NASA has confirmed that the February launch window is no longer available. At the earliest, this lunar mission will now target a launch in early March. The wet dress rehearsal can be thought of as a preview of the mission itself. It simulates nearly every step that will occur on launch day, with the sole exception of engine ignition and liftoff. Because several components are expendable, this test carries added significance. This includes the two massive solid rocket boosters, often compared to white-suited bodyguards, standing beside the core stage. Since they use solid fuel, they cannot be drained and refilled like liquid-fueled systems. Once used, they must be replaced. A successful wet dress rehearsal will ultimately determine when the mission can launch. When launch day arrives, the sequence of events will closely mirror everything that was tested during this rehearsal. The key difference is that this time, 4 astronauts will be involved. After completing a period of quarantine, they will arrive at the launch site and board the spacecraft. Even then, emergency exit procedures will remain in place up until the final moments. Then comes the moment many have been waiting for years. The SLS will ignite and begin its journey toward the moon. The mission will last approximately 10 days. About 1 day will be spent in Earth orbit, followed by 4 days traveling from Earth to the moon. The spacecraft will spend roughly 1 day performing a lunar flyby before using the remaining 4 days to return home. If you're wondering about the finer details, don't worry. Those answers are coming next as we move into a closer look at the major new features and changes that set Artemis 2 apart from human spaceflight missions of the previous century. The first major difference is the journey to the moon itself. This mission will not follow the same profile as Artemis 1. That uncrewed flight lasted 25 days and included multiple orbits around the moon. As mentioned earlier, will only last 10 days. This shorter duration is better suited for a crewed flight. In fact, the total length of most Apollo crew missions was roughly comparable to the timeline planned for Artemis 2. Because the duration is shorter, the overall trajectory is also different. In Artemis 2, after launch, booster separation, and the initial perigee raise burn, the vehicle will perform an additional apogee raise burn. Both of these maneuvers will be carried out by the Interim Cryogenic Propulsion Stage, also known as the ICPS. After completing its role, the ICPS will separate from the Orion spacecraft, marking the end of its mission. This differs from Artemis 1, where the ICPS performed only the perigee raise burn, and then assisted with the translunar injection burn before separating. In Artemis 2, the translunar injection burn will instead be performed by Orion's own engine. This change leads directly to a different mission route. During Artemis 1, the spacecraft headed toward the moon shortly after this sequence. In Artemis 2, Orion will remain in Earth orbit for the entire day to conduct a series of system checks. These include a proximity operations demonstration that takes place immediately after separation from the ICPS. This 2-hour process will evaluate Orion's proximity operations capabilities and manual handling characteristics. This demonstration occurs before the ICPS fully departs from the spacecraft. After separation, Orion will enter high Earth orbit. While in this orbit, the crew will carry out detailed checkouts and evaluations of the life support system, exercise equipment, habitation systems, and other onboard hardware. On the second day, the spacecraft will return to the location of the earlier perigee raise burn. Instead of continuing to orbit Earth, the Orion engine will perform the translunar injection burn, allowing the spacecraft to leave Earth orbit and begin its 4-day journey to the moon. This extended checkout phase was not part of Artemis 1. Because Artemis 2 carries a crew, every system must be verified while still close to Earth. The lunar orbit profile is another major difference between the two missions. During Artemis 1, the spacecraft executed an outbound trajectory correction burn that led to an outbound powered flyby at an altitude of approximately 105.5 miles or about 170 kilometers above the lunar surface. This maneuver placed the spacecraft into a distant retrograde orbit. The distant retrograde orbit involved a half revolution lasting 6 days, which significantly extended the mission. The average distance of this orbit was more than 43,000 miles or roughly 70,000 kilometers from the Earth. Afterward, the spacecraft performed a departure burn and several additional maneuvers to leave lunar orbit. In Artemis 2, the mission profile is simplified to provide a more direct path for the crew. The spacecraft will not perform an outbound powered flyby, nor will it enter a distant retrograde orbit. Instead, following the translunar injection burn, Orion will begin a 4-day outbound transit along a free return trajectory. During this phase, the spacecraft will travel toward the far side of the moon, passing at a distance of about 4,800 miles, or roughly 7,700 kilometers above the lunar surface. This portion of the mission will last approximately 1 day. Notably, this phase requires no engine burns. Instead, the spacecraft will rely on the moon's gravity to naturally curve its trajectory and send it back toward Earth. This approach significantly conserves fuel for the remainder of the mission. Following the lunar flyby, Orion will perform a return trajectory correction burn to properly align itself for the journey home. The spacecraft will then begin its 4-day return to Earth. Upon arrival, the capsule module will separate from the service module. The capsule will descend through Earth's atmosphere, deploy its parachutes, and be recovered by the recovery team. Overall, the Artemis 2 mission is simpler and more direct than Artemis 1 because it carries a human crew. Like Apollo 8, the astronauts will not land on the moon, but will instead spend a day flying past it. Even so, the mission will be no less historic. In addition to providing a close view of our natural satellite, Artemis 2 will gather critical data to support future crewed lunar landing missions. That covers the journey. Now, let's take a closer look at the vehicle. When comparing Artemis 2 to Artemis 1, the most significant changes are in the Orion spacecraft. Designed to carry a crew, Orion will fly with many systems fully active, most notably the Environmental Control and Life Support System. ECOLS provides breathable air, water, waste management, temperature control, carbon dioxide removal, and other essentials needed to sustain astronauts throughout the mission. Dedicated crew communications are also in place. The heat shield has been upgraded using Artemis 1 data, and unlike the fully autonomous first flight, Orion on Artemis 2 can operate both automatically and under direct manual control. The launch vehicle remains the SLS, the same rocket used for Artemis 1 and one of the tallest ever built. SLS features a 2-stage liquid hydrogen and liquid oxygen core, flanked by 2 large solid rocket boosters. Above the interim cryogenic propulsion stage sit Orion and its launch abort system. While it replaces the Saturn V, SLS draws much of its heritage from the Space Shuttle, particularly in its core stage and twin boosters. Together, Artemis 2's vehicle represents an evolution beyond both Apollo and Artemis 1. SLS will continue flying future crewed missions and serves as the basis for later versions like Block 1B. At the same time, the program remains heavily criticized. Development has been slow, with Artemis 1 taking roughly a decade to reach launch, and costs remain exorbitant. Each SLS launch is estimated at around $4 billion, exceeding the total development cost of many other rockets. Quality concerns persist as well, highlighted by unexpected wear found on Orion's heat shield after Artemis 1, an issue that required extensive investigation before Artemis 2 could proceed. Finally, the crew. Artemis 2 will carry humans closer to the moon than at any point in more than 50 years. The 4 astronauts selected are Reed Wiseman as commander, alongside Victor Glover, Christina Koch, and Jeremy Hansen. It's the first lunar mission crew to include both Black and female astronauts, underscoring a more inclusive era of human spaceflight. Each was chosen for their experience, skill, and readiness for a mission of this significance. The crew will also fly with a new generation of spacesuits developed by Axiom Space. Featuring a blue and orange design aligned with NASA's modern identity, these suits differ sharply from Apollo and Shuttle era designs, emphasizing lower weight and more advanced technology. For Artemis II, these suits are intended for intravehicular use inside the spacecraft. Extravehicular suits, also developed by Axiom, are planned to debut with Artemis III. These elements help define Artemis II as the mission draws closer. It's fair to say that NASA has navigated significant controversy to reach this point. As discussed earlier, schedule delays, high costs, and concerns over reliability have been the three primary sources of criticism. These issues were serious enough that NASA's systems were included in proposed budget cuts earlier this year. Now that the mission is approaching launch, attention naturally shifts toward reliability. Early concerns became evident during the first wet dress rehearsal, and unresolved questions surrounding the Orion heat shield have continued to trouble the aerospace community. Because of this, NASA must focus on executing every remaining step with precision. Doing so is essential to ensure that the time, effort, and funding invested over the past years are not squandered. Looking ahead, the long-term picture will be different. Although NASA's core systems have been preserved and will continue to play a central role, particularly in coordination with commercial partners for lunar landing missions, further adjustments are still required. Improvements in reliability, production speed, and cost efficiency are critical for sustaining a long-term return to the moon. Beyond its in-house programs, NASA must also continue to support and encourage its commercial partners, including companies such as SpaceX and Blue Origin. Recent visits and public statements from Isaacman expressing strong support for these efforts suggest positive momentum in that direction. Above all, progress depends on data, and the most valuable data will come from Artemis II itself. That is what the entire community is waiting for. We have now covered the mission in full. All that remains is to watch and to be ready to experience it when it finally arrives. We are getting closer to the moon, both in time and in distance. After years of waiting, NASA has rolled the SLS onto the launch pad. However, the path to a 10-day journey to the moon remains challenging, as significant work still lies ahead. Here is what NASA must accomplish before the journey can begin. So, let's find out more on today's episode of Great SpaceX. NASA delivered an exciting and consequential weekend, marking the rollout of its second lunar mission vehicle after more than 3 years of preparation. This moment represented far more than a simple move across Kennedy Space Center. It was a visible signal that the next chapter of human lunar exploration is nearing reality. The rollout itself was a remarkable sight. The fully assembled SLS, or Space Launch System, standing approximately 98 meters tall, was transported vertically from the Vehicle Assembly Building, or VAB, to LC-39B. This made it the tallest object ever moved since the era of the Saturn V. At the launch pad, both the rocket and its supporting ground systems must undergo a series of rigorous evaluations. These tests are designed to validate not only the performance of individual components, but also the way those components function together as an integrated system. The first major test in this sequence is the radio frequency interference test. Ideally, radio frequency interference testing is performed inside controlled environments such as shielded chambers or specialized vacuum facilities. However, conducting this test at the launch pad is essential because the pad provides conditions that can't be replicated inside the VAB. At the pad, the spacecraft is exposed to real-world operational factors that closely resemble those it will encounter during launch and flight. The purpose of the radio frequency interference test is to ensure that all onboard systems can operate simultaneously without disrupting one another. It also verifies that the spacecraft can withstand interference from external sources. This capability is critical for both uncrewed and crewed missions, especially in the harsh and unpredictable electromagnetic environment of space. The launch pad environment enables several key aspects of this test. The open area around the pad allows engineers to use actual antennas and to communicate with external networks, such as the Tracking and Data Relay satellite system, the Deep Space Network, and other ground-based tracking stations. This test also includes end-to-end communication checks, which are vital for mission control operations. Equally important is the presence of ground support equipment and umbilical connections, which can introduce interference that does not exist in laboratory settings. These real-world variables make pad-based testing indispensable. Once radio frequency testing is complete, the next major milestone is cryogenic fuel loading. During this process, liquid propellants will be loaded into the core stage and upper stage tanks. These propellants include liquid oxygen and liquid hydrogen, which must be stored and transferred at extremely low temperatures. Liquid oxygen is maintained at temperatures below -183 degrees Celsius, while liquid hydrogen must be kept below -253 degrees Celsius. This test evaluates the ability of the tanks, valves, and transfer lines to safely contain and manage cryogenic propellants. Of particular concern is liquid hydrogen, which is the smallest and lightest element. Its physical properties make it especially prone to leakage, even through microscopic imperfections. As a result, hydrogen systems require exceptional precision and reliability. The importance of this test is underscored by past experience. During the Artemis 1 campaign, a liquid hydrogen leak contributed to significant delays, ultimately pushing the launch to November of 2022, despite testing that began months earlier. With a much tighter schedule for this mission, NASA is determined to identify and resolve any similar issues as early as possible. In addition to leak detection, the cryogenic loading test allows engineers to evaluate the performance of the fueling systems themselves. This includes assessing pumping rates, flow stability, pressure control, and overall system responsiveness. These factors directly influence the timing and reliability of the launch countdown. Accurate data from this test will help refine procedures and reduce uncertainty during the final launch sequence. All of these activities share a common objective: safety. As the testing campaign progresses, the focus increasingly shifts toward operations that directly involve the crew. An especially important component of the wet dress rehearsal is the emergency evacuation exercise. In this scenario, astronauts simulate a rapid exit from the spacecraft and travel to a safe location. Although such a procedure is only intended for rare and hazardous situations, it is an essential safeguard. Practicing this sequence ensures that both the crew and ground teams are fully prepared to respond decisively if conditions demand it. NASA has taken extensive measures to protect the crew from the effects of cryogenic fueling operations. According to Artemis launch director Charlie Blackwell Thompson, these systems have been tested independently to ensure that they are not affected by the extreme thermal environment created during tanking. She expressed confidence that the team would be fully prepared for the wet dress rehearsal. The wet dress rehearsal effectively serves as a full-scale preview of launch day. The countdown will proceed all the way to T-minus 29 seconds, stopping just short of engine ignition. By executing nearly every step of the launch sequence, NASA can identify any procedural or technical issues that might otherwise go unnoticed until the final moments before liftoff. One notable absence from the testing campaign is a static fire test. This omission is intentional. The SLS relies on two large, solid rocket boosters that provide the majority of thrust during liftoff. Unlike liquid engines, solid rocket boosters cannot be shut down or reused once ignited. Conducting a static fire would require sacrificing and replacing these boosters, which would be impractical and unnecessary. Instead, each booster has already been tested individually prior to integration with the vehicle. This sequence of tests represents the final stretch before the crew embarks on their 10-day journey around the moon. Understanding the importance of this process requires recognizing its direct influence on the launch schedule. To accommodate these uncertainties, NASA has established multiple launch windows spanning February, March, and April. Each window consists of several days, providing flexibility to respond to technical findings while preserving the mission's overall objectives. After years of development and preparation, the upcoming test campaign demands unwavering focus from NASA and its contractors. Any lapse in execution could undermine the immense investment already made. That investment has not gone unnoticed. The SLS, Orion spacecraft, and supporting infrastructure have cost tens of billions of dollars. Artemis 1 alone required nearly a decade of preparation. Throughout this time, the program has faced intense scrutiny, particularly regarding reliability and cost effectiveness. Issues such as heat shield performance have fueled criticism and skepticism. At various points, these concerns led to proposals that would have canceled or significantly altered the program during budget reviews. Although Congress ultimately preserved the program, continued support depends on demonstrable progress and success. Strong performance during testing and operations is essential to justify the program's future. Beyond domestic considerations, Artemis II also carries international significance. The mission unfolds against the backdrop of growing global competition in space exploration. China, in particular, has made substantial advances, including successful lunar landings on both the near and far sides of the moon and the return of lunar samples to Earth. These achievements support its ambitions for crewed lunar missions and the construction of a sustained presence on the lunar surface. While the U.S. achieved crewed lunar landings decades ago, those missions were brief visits. The current objective is fundamentally different. This time, the goal is to establish a lasting presence. Achieving that goal requires sustained leadership, technical excellence, and consistent progress. Although Artemis II does not include a lunar landing, it plays a vital role in validating systems and procedures for future missions. The data collected during this flight will inform subsequent crewed landings and shape the timeline for establishing lunar infrastructure. Once preparations are complete, the mission will enter its most critical phase. After liftoff from Florida, the spacecraft will ascend through Earth's atmosphere, separate from the first stage, and execute a burn to raise its orbit. Following separation from the second stage, Orion will perform a series of system checks in Earth orbit before initiating the translunar injection burn that sends it toward the moon. This outbound journey will take approximately 4 to 5 days. Upon arrival, Orion will spend about 1 day orbiting the moon. During this time, the crew will be closer to the lunar surface than any humans have been in more than 50 years, reaching a distance of roughly 7,400 kilometers. In addition to observing the moon, the crew will conduct experiments and system evaluations that are essential for future missions. The return journey will take advantage of lunar gravity. By carefully navigating around the far side of the moon, Orion will use a gravitational slingshot maneuver to redirect its trajectory toward Earth. This technique conserves fuel while maintaining precise control over the spacecraft's path. The trip back to Earth will take roughly 4 days, with course corrections performed as needed. The mission will conclude with re-entry into Earth's atmosphere, where Orion will endure extreme heat and forces before splashing down in the Pacific Ocean. This moment will mark the successful completion of the second phase of the Artemis program. We are now very close to Artemis II. It represents the first crewed lunar mission in more than half a century and a crucial step toward future landings and a permanent human presence on the moon. NASA, the SLS, Orion, and 4 astronauts stand ready. Challenges remain both before launch and during flight, but overcoming these challenges is how humanity proves its ability to explore beyond Earth. Everything is in place. The question now is simple. Are we ready to go? In any case, folks, this has been Kevin with Great SpaceX. Don't forget to like the video and subscribe if you haven't already to stay up to date with yours truly on the latest milestones in SpaceX's journey. Thank you so much for watching, and always remember, curiosity, imagination, and inspiration will follow you so long as you keep looking up.